So in this next lecture, we're going to talk about topics of absorption and dispersion of electromagnetic waves on some interface. So this is section 9.4 in Griffith's book on electrodynamics. So the idea is that now we're going to loosen our constraints and say what happens if we have an electromagnetic wave which is now incident on a material. So this is material 1, this is material 2, but this material now is a conductor. So our intuition tells us that the electric fields and magnetic fields in the wave, once they hit that conductor, they are going to now create forces which are going to move charges around, since charges are allowed to move freely inside of a conductor. And so what we're going to do is we're going to start with Ohm's law, which basically says the current that we're going to create is equal to the conductivity times the electric field. So that electric field is now going to move those charges and create a current. So if this is a linear medium, we can write out Maxwell's equations. So this is the free charge density divided by epsilon. So it's not epsilon naught. So this is the permeativity of the medium, of the material, this conductor. The second equation is always 0. The Maxwell's third equation now is the same as it was when we were just talking about with an insulator. And then Maxwell's fourth equation now includes the current. So mu times the current, which we said from Ohm's law is the conductivity times the electric field, plus mu epsilon times the change in the electric field with respect to time. Okay. The other thing we need to consider is applying Ohm's law to the continuity equation. So the continuity equation says the divergence of the free current is going to be equal to minus the change in time of the charge density. Now the free current is just the conductivity times the electric field, that's a constant that doesn't change in time, or it doesn't change what charge is conserved. So there is no change in the conductivity. And so, I should say that we're dealing with a uniform medium, so there is no change in the conductivity of it. So in the end, what we get is the conductivity times the divergence of the electric field, which from Gauss's law, or Maxwell's first equation, that becomes minus the free charge density over epsilon. So in the end, what we have is this equation where the derivative with respect to time is equal to the conductivity divided by the permeativity times the charge density. So that's a pretty simple differential equation to solve. So what we get is the charge density as a function of time is equal to E times minus I, the conductivity divided by the permeativity, times time, and all of that times some amplitude. So basically the initial condition, how much charge do we start with, and then how does it dissipate. So in the end, once we liberate charge inside this medium with our magnetic field, we're going to get some charges that accumulate, and then they're going to start moving around and dissipating into the medium. They're going to start combining and neutralizing. So we have some initial amount of charge, and then it's going to dissipate over time. Exponentially, like this. Okay, so we can now quantify basically a time constant for how well a medium is conductive, and that time constant we'll call tau is just the permeativity over the conductivity. So our equation then becomes that right there. Okay, so like I said, this tells us how good a conductor it is, because if the conductivity was infinite, then the time constant would be 0. The charges would instantaneously spread out and neutralize. If this conductivity is much, much less than infinity, so you're kind of in the middle, then our time constant is not going to be 0. It's going to take some time for those charges to make their way through the conductor. So now, this time constant gives us a handle, or either way around. You can just say, given the quality of the conductor, we can figure out how much time it takes for the charges to dissipate, or measuring how long it takes the charge to dissipate, we can actually determine what kind of a conductor it is. So if we now go to the point right over here, where the basically we let the charge go back to 0. So essentially, after a long time, then this will go to 0. And what do we get in terms of Maxwell's equations? Well, we would get the first equation says there's no free charge anymore, so the divergence is 0. Divergence of the magnetic field is always 0. The curl, Maxwell's third equation, of the electric field is still this. And the interesting one is the curl of the magnetic field now is you still have the time derivative electric field, but you also now have mu sigma times the electric field. So the electric field is still there, even though the free charge had dissipated. So essentially what we're saying is that even if the charge goes out and neutralizes inside the conductor, we're still going to have the possibility of a current. And this is what's different from all the previous derivations we did in this chapter, where we're talking about insulators. Now we're talking about conductors, where the free charge is gone, has left, but the current can still remain behind. Okay, so now what we want to do is we want to go back and come up with a wave equation for this. And so we're going to do it in the same manner, where we take the curl of the electric field, or the curl of the magnetic field, and we can follow the same derivation from earlier in the chapter, and what you should get is this Laplacian So that's the same equation we got for the insulator, but we now have a first order time derivative included. And the same thing is true with the magnetic field. So again, I'm not going to go through that derivation, but what you find is you get this first order time derivative in the equation. So this is our new wave equation. This is the equation we have to solve. So it turns out the solution to this, to these equations, in complex form, in one dimension, basically propagating in z, is the amplitude of the field e to the I k, where I'm now going to put a squiggle on it, times z minus omega t, or b, magnetic field, is the amplitude e to the I squiggle k, or tilde, I guess, if you want to call it. So what we get is this constant that's related to the position is mu epsilon omega squared plus I mu sigma omega. So it's now a complex wave number, which we can now write down as the real part that we had when it was an insulator. It's an insulator, then sigma is equal to 0. But what we get is a real part plus an imaginary part. We're now going to put that constant as kappa. Okay, so that means, if I put this all together, that k is equal to epsilon mu divided by 2, 1 plus sigma over epsilon omega squared square root plus 1. And I take this, so basically I'm finding the amplitude of it. I'm finding, well, the norm. And then for kappa, I get omega square root epsilon mu over 2, 1 plus sigma epsilon omega quantity squared, square root of that, minus 1, and then I take the square root of that. So in working our way through this, what you get is some kind of complicated looking equations with square roots inside of square roots. But essentially, what's the interpretation of this? Well, the interpretation of this is that the constant kappa basically what tells us how much the wave dissipates in the z direction. So if I was to basically put all this together, I would get the original amplitude of the wave. I could pull out the kappa part, and then I would get I times I, which gives me a minus 1, e to the I k, the original k wave number, minus omega t. And the same thing for the magnetic field. So essentially, that exponential causes our wave in space. Let's say this is the amplitude of the electric field. This is our exponential. We would get a damped wave like that. The electric field, as it goes into the conductor, it starts to now lose strength and dissipate and get reduced in amplitude the deeper and deeper it goes into the conductor.